Welcome. Today we're going to go into some more detail on some of these theorems to show you how to build up a more detailed table of Laplace transforms, for example, and to be able to do some more difficult or challenging problems involving step functions. All right, so remember that this is the whole reason that we want to use Laplace transforms is so that we can handle differential equations in which there's a step function in them. Okay, because otherwise you've got other possibly simpler methods to solve differential equations than Laplace transforms. I'm going to pull up my little table of Laplace transforms and their inverses. All right, so generally what we want to do is use a table to help us solve differential equations, or a table of Laplace transforms, by looking up the things we need in a table like this one and writing down the Laplace transforms. So like in previous sections we've derived Laplace transforms, and that's totally fine, but in the end it's faster to look these up in a table. Okay, but your table is almost never complete. And so I'm going to show you how to do some of these things yourself when you don't have a full table, right? Because it is fairly easy to calculate the Laplace transform and the inverse Laplace transform of various things when you have these nice theorems over here. All right, so I'll put this down for now, and let's have a look at some step functions. Right, and up to this point you would know these as piecewise functions. So solving equations with step functions in them. So recall the Heaviside step function or Heaviside theta function is defined as 0 if t is less than 0 and 1 if t is greater or equal to 0. But I'll remind you that some authors put, let's write this here, some authors and even computer software put u of 0 to be undefined. Okay, so from that point of view, some things are slightly different, but I'm using, for this section, I'm using the reference called differential equations. Blanchard, Devani, and Hall. That's the text I'm using, differential equations. So they have this definition for the Heaviside theta function or Heaviside step function. All right, so let's think about this here. We've got u of t on our y-axis, and down here we've got t on our x-axis. Okay, and so it's off, and then it's suddenly on. All right, so it's 0. This is u equals 0 down here. This occurs when t equals 0, the change that is. And so this is open because that shows that it's, the t equals 0 part is here, up here. So it's open down here and it's filled in up here. Okay, so this is on where u is equal to 1 and it's off down here. It's like you just flip a switch, right? It's off, and then at some point in time, it's on. Okay? Now, we can think about other step functions where the switch happens at a different t value. So, for example, if t equals 2 is where the turn on happens, then this is happening at t equals 2, and up here we have u equals 1. This is u of t. Down here, u is equal to 0 until you get to t equals 2, and then it's suddenly on, or u equals 1 at t equals 2, and it remains 1 from then on. Okay, now more generally, if we translate this Heaviside theta function, u of t minus c is 0 if t is less than c, and it's 1 if t is greater or equal to c. Okay, but from that we can also introduce a step down function. So the step down function, so this being t, and then we might have a u-axis here and an origin there, for example. All right, so suppose that this change happens at t equals c. So it's on, say u equals 1 up here, and then suddenly you turn the switch off when t is equal to c, and down here we have u equals 0, and it stays off. Okay, so using this step down function, and it's 1 minus u of t minus c, where u of t minus c is given by this. So using the step down function, we then have the ability to take a piecewise function and recognize that in terms of the Heaviside step function, or Heaviside theta function. So let's define f of t equal to its piecewise function t squared if t is greater or equal to 2. Now this is t equals 2 where this happens, that jump. And let's put minus 3t if t is less than 2. So here we've got minus 3t, and up here we have t squared. And that's open down the end. All right, so now recognizing this in another way, in terms of the Heaviside function, we have t squared multiplied by u of t minus 2, right? And this says it's 0 on the left of t equals 2, and then suddenly this is on, and so t squared times 1 is t squared. All right, but there's more, because we have a left-hand side of t equals 2 to deal with as well. All right, on the left-hand side, we have minus 3t, and then we can multiply this by 1 minus u of t minus 2. So the step-down function. All right, so our piecewise function can be represented in this way. And now, look at this, we can expand and collect like terms. So expanding this, we have t squared minus 3t times minus u of t minus 2. So that's plus 3t, and then all times u of t minus 2. And then expanding this part, we have minus 3t. Okay, fantastic. So that's what we have right here, just the expansion of this. Now, how do you take the Laplace transform of a step function? So remember, since it's off before we get to c, this whole thing here is 0 until we get to c. So what we have then is this is the integral from c to infinite of e to the minus st times 1, because suddenly when it turns on, it's 1 there at c, but it's 0 before it. Okay, dt. All right, and so we can integrate this, and our integral here is e to the minus st divided by 1 on minus s. And now we need to evaluate this between 0 and infinite and take the difference. All right, but since that's infinite up at the top, we need to do this via a limit. But let's remind ourselves first, it's this because 0 before t equals c, and 1 after. Okay, now let's evaluate this. Again, we need to do this via a limit. So we have the limit, as t goes to infinite of 1 over minus s, e to the minus st, and then we are subtracting what happens when we sub in t equals 1. So let's put in a bracket, 1 over minus s, e to the 0. Okay, now this limit right here, as t goes to infinite, is 0 because, you know, taking this downstairs, you're putting in or imagining that you are putting in a very large number, right? And so we have 1 over a very large number when s is positive. So this limit gives 0 when s is positive, and then simplifying this, we have plus 1 on s. All right, so this is valid for the real part of s being positive. Okay, and so for that we have 1 on s. Okay, so that allows us to calculate this now. So the Laplace transform of 1 minus u of t minus c, because we have linearity here, we've got the Laplace transform of 1 minus the Laplace transform of u of t minus c, which we've just calculated above. Yeah, that's right. So I forgot, that's a c. Okay, that's a c. And so this makes this a cs minus cs, and that puts a minus cs here. And hence e to the minus cs here as well. Okay, so now back to this. The Laplace transform of 1 is 1 on s, and then the Laplace transform of this, well, we've got this, but we have a minus in front, minus 1 on s, e to the minus cs. Okay, second shifting theorem. It says that the Laplace transform of a function of t minus c times the step function at t minus c is equal to e to the minus sc times the Laplace transform of f of t. And the inverse Laplace transform of e to the minus cs times uppercase f of s is lowercase f of t minus c times the step function u of t minus c, where lowercase f of t is the inverse Laplace transform of uppercase f of s. So let's have a look at an example here. Calculate the Laplace transform of t squared times u of t. So f of t being t squared. So here c is 0. So what we're doing then is taking the Laplace transform t squared u of t to be equal to e to the power of 0, just using this, c is 0, and then multiplied by the Laplace transform of t squared. Now the Laplace transform of t squared is 2 over s cubed. So we have 2 over s cubed for the Laplace transform of t squared times u of t. Okay, moving on. Let g of t be this piecewise function. Now this is, I think that this is what we calculated earlier. Yeah, so it's this piecewise function, right? So I should have said that this is g. But anyway, let's leave that for now. Okay, so we're just looking at this, which is all of this, all right? So show that f of t is t squared plus 7t plus 10. Show that it satisfies this, and then use the second shifting theorem to calculate the Laplace transform of this. Okay, so we want to start off with f of t minus 2. So f of t minus 2 with f being this, is t minus 2 squared plus 7 times t minus 2 plus 10. Okay, now expanding, we have t squared minus 4t plus 4 for the expansion of t minus 2 all squared, and then plus 7t minus 14, and then plus 10. All right, so collecting like terms, we have t squared minus 4t plus 7t is 3t. And then 4 minus 14 is minus 10, plus 10 is 0. Okay, so this is what we do have. F of t minus 2 is t squared plus 3t. Now let's use the second shifting theorem to calculate the Laplace transform of g of t. So Laplace transform of g of t is the Laplace transform of, now g of t being f of t minus 2 from this identity here, multiplied by u of t minus 2, and then minus 3 times the Laplace transform of t. So again, we're using linearity on that, meaning that the Laplace transform of a sum is the sum of the Laplace transforms. All right, so next, let's have a look at our second shifting theorem. All right, where did this go? It tells us how to do this. So C here, that's right, C equals 2 in the second shifting theorem. So this tells us how to calculate this. So we have, for this one right here, e to the minus sc, so minus 2s, times the Laplace transform of f of t okay, and then minus 3 times the Laplace transform of t. All right, so f of t, remember, was t squared plus 7t plus 10. So we need Laplace transform of t squared plus 7t plus 10. Okay, so now we can go and look up our table of Laplace transforms, which we derived earlier. So the Laplace transform of t squared is 2 over s cubed. And then we have plus 7 times the Laplace transform of t, so 7 over s squared. And then the Laplace transform of 10 is 10 over s. Laplace transform of t is 1 over s, so we have minus 3 over s. Okay, and so now we have taken the Laplace transform of g of t using the second shifting theorem. Okay, so next, let's consider an applied example. Consider the RC circuit modeled by the equation 2 dv on dt plus v is 3 times the step function u of t minus 2. All right, and so this is in the book by Blanchard, Devaney, and Hall, Differential Equations. It's chapter 8. So they go into more detail on this and show you a nice diagram. I'll just focus on the mathematics. So use the shifting theorem, second shifting theorem, to solve this equation. All right, it's a bit tricky. So first up, we want to say let uppercase y. You could use uppercase v for this, but you have to be careful, right? Yeah, let's go ahead and use uppercase v. You got to be careful to say that it's an uppercase, because uppercase and lowercase can look similar when you write them by hand. So let that be the Laplace transform of lowercase v of t. So put little n's on this. Okay, so there we have that. So then the Laplace transform of our left-hand side, which is 2 lowercase v dash of t plus v of t, is equal to the Laplace transform of the right-hand side, but remember the 3 can come out, so we have 3 Laplace transform of u of t minus 2. Okay, so we've just taken the Laplace transform of both sides. Now on the left we have twice the Laplace transform of v dash, but the Laplace transform of v dash is s times uppercase V of s minus lowercase v of 0. Okay, and on the right hand side we have 3 times the Laplace transform of that step function, and remember that that was 1 on s e to the c, which is or minus c, so minus 2s. Okay, fantastic. So v of 0 is 4. So on the left we have 2s uppercase v of s. 2 times 4 is 8, so minus 8. And then on the right hand side we have 3 over s e to the minus 2s. Okay, so now we want to take the 8 over to the right hand side and divide everything by, oh hang on, what have I done here? I've forgotten the Laplace transform of this one, so that is plus an uppercase v of s there. Okay, so in here then, factorizing the uppercase v of s out, we have another 1 there. Okay, so we want to take the 8 over, divide both sides by 2s plus 1, so that we have solved for uppercase v of s. Let's do that next. Uppercase v of s is equal to 8 over 2s plus 1 plus 3 over s 2s plus 1 e to the power minus 2s. So we have now solved for uppercase v of s, and next what we need to do is take the inverse Laplace transform of both sides. So taking inverse Laplace of both sides of the equation that we have above, then we get lowercase v of t is the inverse Laplace transform of uppercase v of s, which is, now incidentally, before we do this, we want to sort of tidy this up, and by tidied up I mean make it recognizable in your table of Laplace transforms. So in other words, this one right here, we can divide top and bottom by 1/2. So we would have 4 over s plus 1/2, but plus 1/2 we can write as minus 1/2, so that it's recognizable in the table of Laplace transforms. And this one for now we'll leave it as is, but we want to separate that with partial fractions before we fully take its inverse Laplace transform. Okay, so here we are taking the inverse Laplace transform of this one. So 4 over s minus 1/2, and then plus 3 times the inverse Laplace transform of 1 over s 2s plus 1 e to the power of minus 2s. Okay, now we want to separate this out by partial fractions. Am I missing something again? Oh, never mind. I see what's going on. Okay, so the partial fractions part. Okay, so via partial fractions on this, which is pretty tricky. So using partial fractions, what we have then is lowercase v of t is the inverse Laplace transform of, and we can pull the 4 out right now, so 1 over s minus minus a half, and then plus 3 over, or inverse Laplace transform of 3 over s e to the minus 2s. And so I've just broken this up using partial fractions, but I won't show you the details of this. Then minus 6 over 2s plus 1 e to the minus 2s. Okay, so that's this part of it. Now, this is recognizable in the table of Laplace transforms, but this one not quite yet. We have to express that denominator as s minus 1 on 2. But when we do that, we divide top and bottom by 2. Okay, and so now we can look this up in the table of Laplace transforms and get 4 times e to the minus a half t for this one. And then for this one, we'll get plus 3u of t minus 2 times f, lowercase f of t minus 2 for this using the second shifting theorem, and I'll remind you of that. All right, so what we're looking at is this inverse Laplace transform of e to the minus cs times uppercase f of s. This is our uppercase f of s in this, and this is our e to the minus cs. So c here is 2. So it says that we should have this, right, which is what I have got here, where inverse Laplace transform of that uppercase f of s is lowercase f of t. Okay, great. So that's f of t minus 2 there. And then for this one, again using the second shifting theorem, this second line, we will get minus 3u of t minus 2 g of t minus 2. Okay, where, and this is not necessarily the same f and g as we have before, is it? So not same f and g as earlier necessarily. So I should say earlier. Okay, and so where f of t is the inverse Laplace transform of 1 on s, so in other words 1, and hence f of t minus 2 is 1, and g here is the inverse Laplace transform of the part here without the 6, which is 1 over s minus minus a half. So e to the minus 1/2 t. And so g of t minus 2 is e to the 1 minus a half t. All right, so this is what goes there, and this is what goes there. All right, which does give a solution. I just need a little bit more paper for this. but maybe I can smash it in below. So we have 4e to the minus a half t plus 3 times the step function u of t minus 2, and then f of t minus 2 is 1, so we just have 1 there. Next, minus 3 u of t minus 2. G of t minus 2 is e to the 1 minus 1/2 t. All right, and this is our answer, or our solution to the differential equation. Okay, next we're going to look at the convolution theorem. So this is a way to calculate the inverse Laplace transform of a product. And so to do something that may not be in your table or may be in your table of Laplace transforms or inverse Laplace transforms. So let's start with an example, but first we need to look at the theorem. So here, incidentally, tau, it looks like a T, but this is tau, it's a Greek letter. And so the inverse Laplace transform of a product of uppercase F and times uppercase G, both functions of S, is an integral of f of tau times g of t minus tau with respect to tau, from tau equals 0 to tau equals t. Now that's lowercase f of tau and lowercase g of t minus tau, where lowercase f of t is the inverse Laplace transform of uppercase f of s, and lowercase g of t is the inverse Laplace transform of uppercase g of s. Okay, so the two things inside, you've got to invert Laplace transform, and then once you have these inverse Laplace transforms, you can calculate the integral there. All right, so let's have a look at this first example, 7.12. Calculate the inverse Laplace transform of the product of f and g, where f is 1 over s minus 1 and g is 1 over s plus 2. So first we start with the inverse Laplace transform of 1 over s minus 1, and this is our f of t. And so if you just look this up or calculate this, we have e to the power of t. Okay, now for g of t, that's the inverse Laplace transform of uppercase G, so 1 on s plus 2. And so for this one, we have e to the minus 2t. Okay, and so let's have a look. We need f of tau, so f of tau is equal to e to the power of tau. G of t minus tau, according to that, is e to the minus 2 t minus tau. Okay, so now we need to calculate the integral from tau equals 0 to tau equals t. I recommend setting these out because it's a little confusing between t's and taus. We're integrating with respect to tau. Okay, so we have f of t, that's e to the tau, and then g of t minus tau is e to the minus 2 bracket t minus tau, and we're integrating this product with respect to tau. Okay, so to do this, you might want to add the exponents, and so we're integrating from t equals tau to t equals, from tau equals 0 to tau equals t, e to the power of tau plus minus 2t plus 2 tau. So if we expand this, we have 2 tau, and then adding tau gives us 3 tau. And then we have e to the power of minus 2t. Okay, d tau. Now remember, when we're integrating with respect to tau, we're thinking of this as a partial integral, so this we're treating as a constant when we integrate. Okay, so this integral then is we still have e to the minus 2t, treating that part as a constant, and then we have e to the 3 tau integrating with respect to tau. But if you think about the derivative of e to the 3 tau with respect to tau, you would pull down a 3, so we need to divide by this 3, right? And so this is our integral, but then we're taking this from tau equals 0 to tau equals t. Okay, great. So next we have to sub in replacing tau with t and replacing tau with 0 and take a difference. Now this one just hangs out at the front. So we have 1/3 e to the minus 2t and then brackets e to the 3t minus e to the 0, which will give us 1/3 e to the sum of these exponents, which is t, and then minus 1/3 e to the minus 2t, because e to the 0 is 1. Okay, fantastic. So this is our inverse Laplace transform, and if we get Mathematica to check this, which we can here, we'll just say, okay, Mathematica, what is the inverse Laplace transform of 1 over, down the bottom we have s plus 2, and then we have s minus 1. Okay, so it gives us this, but let's look at the expanded form. So we'll just say expand this, please. You don't have to say please. It just does it. Okay, so e to the t over 3, that's what we have down here, minus 1/3 e to the minus 2t. Okay, fantastic. Let's move on to the next page. And I'll keep this one handy so we can look at our theorem. All right, so I want to calculate the inverse Laplace transform of 3 over s minus 3 all squared. So make sure yours has a numerator of 3. Okay, so to do this, we want to set out an uppercase F and an uppercase G. So let uppercase F of s be one of the multiplicands in here. So let's say 3 over s minus 3, and uppercase G of s, the other multiplicand, thing being multiplied, s minus 3. Notice that the product of these two gives us 3 over s minus 3 all squared. Okay, so now lowercase f of t is the inverse Laplace transform of 3 over s minus 3. And so the 3 can come out. So we have 3 times e to the power of 3t for that one. Now, g of t is the inverse Laplace transform of 1 on s minus 3. And this is e to the power of 3t. Again, you can integrate this or look it up in the table. Okay, so now what we need is f of tau is 3 e to the 3 tau. G of t minus tau, because remember we're going to use these two things in our theorem. So g of t minus tau is e to the power of 3 bracket t minus tau. Okay, so putting this together in the convolution theorem, the inverse Laplace transform of 3 over s minus 3 all squared is equal to the integral from tau equals 0 to tau equals t of the product of these two things. So 3 e to the 3 tau e to the 3 t minus tau in brackets with respect to tau. Okay, fantastic. Now to calculate this, you probably want to add the exponents here. So we have 3 times e to the, now when you expand this, we have a minus 3 tau that we can add together with this one, adding those exponents. So the tau's vanish, and then what we're left with is e to the 3t with respect to tau. And so integrating this one gives us, because we're treating this whole thing as a constant now, there are no taus in it, so we have 3 tau e to the 3t. But that's as tau goes from 0 to tau equals t. And so we sub in, replacing tau with t. So we have 3t e to the 3t minus 3 times 0. And so that's just 3t e to the 3t. Okay, well that was easy enough. You might disagree. All right, let's have a look at our third page. Verify that the inverse Laplace transform of s over s minus 3 all squared is e to the 3 times 3t plus 1 by writing s over s minus 3 squared as s minus 3 plus 3 on the numerator all over s minus 3 squared, and using the table of Laplace transforms or the previous example. All right, so let's use this hint here. So what we have then is inverse Laplace of s over s minus 3 all squared is the inverse Laplace of s minus 3 plus 3 over s minus 3 squared, which is the inverse Laplace transform. Now this, we can view this, breaking this up, we have the inverse Laplace transform of 1 over s minus 3 plus 3 over s minus 3 squared. Okay, and then we have linearity here, meaning we can break this up. The sum of the inverse Laplace transform of the sum is the sum of the inverse Laplace transforms. So the inverse Laplace transform of 1 over s minus 3 plus the inverse Laplace transform of 3 over s minus 3 squared. Okay, this is the thing we calculated in the previous example. Now this one is pretty easy. We just have e to the power of 3t, and then let's copy what we had from the previous example there, that this is equal to 3t e to the 3t. Okay, and we can even factorize this, right, and show that it's what we're meant to have up there. So e to the 3t multiplied by 3t plus 1, just factorizing that result, and that's what we get. All right, but this gives us an opportunity to ask the question, what if we had used the convolution theorem on this directly? Okay, so let's say note, if we instead put f of s is equal to s over s minus 3 and g of s is equal to 1 over s minus 3. Okay, then we would set out, you know, you might take this f of s equal to 1 plus 3 over s minus 3. Okay, and so if you put this back together, you'll see on the top you have s minus 3 plus 3 all over s minus 3. So this is true, this is equal to this. All right, but now if you take the inverse Laplace transform of this, which is what we're meant to do in the convolution theorem, we have the inverse Laplace transform of 1 plus the inverse Laplace transform of 3 over s minus 3. Okay, now the inverse Laplace transform of 1 is the Dirac delta function of t. Okay, and I'll talk about that in a moment. But then we have plus 3 times the inverse Laplace transform of 1 over s minus 3, which is 3e to the 3t. All right, so this gives us an opportunity to talk about the Dirac delta function. So loosely speaking, Dirac delta is defined as just an infinite pulse plus infinite if t is equal to 0 and it's 0 otherwise. So if t is not equal to 0. And of course, other authors might define this differently, and in fact, if I put in Dirac delta here in Mathematica, Dirac delta at 0, it will just return Dirac delta at 0, right? Because obviously it cannot give me this. So this is loosely speaking, right? Now, so let's say that, loosely speaking. Because of course, this is not a number. Okay, and so it satisfies the integral from minus infinite to infinite of delta of t with respect to t is 1. All right, so this is how it's defined, where it's 0 if t is not equal to 0. Okay, and let's say, so you can look this up, Dirac delta function. And again, remember that some authors might define this slightly differently. Okay, so then, now let's talk about g. So g of t is equal to the inverse Laplace transform of 1 over s minus 3, which is e to the power of 3t. Okay, so the inverse Laplace transform of the product, which is s over s minus 3 all squared, is equal to the integral from tau equals 0 to tau equals t of f of tau. So this is Dirac delta of tau plus 3e to the 3 tau, not t, tau. Okay, brackets, because we're going to multiply by g of t minus tau. So this is e to the 3 t minus tau, and then we're integrating with respect to tau. Okay. And so then, you would expand this. The taus in the expansion here would vanish because you could add the exponents. So this part of it would be e to the 3t, but this part over here would be e to the tau times e to the 3t minus tau. And so you'd have to take great care to do this integral, right? So, it gets fairly deep. Okay, let's continue. I mean, I'm happy here, right? But we had an opportunity to talk about Dirac delta for a moment. Okay, example 7.15. Use the convolution theorem to calculate the inverse Laplace transform of 1 over s squared s plus 2. So we might let uppercase f of s be equal to 1 over s squared, and uppercase g of s be equal to 1 over s plus 2, because these are two things that we can take the inverse Laplace transform of quite easily. Okay, so lowercase f of t is the inverse Laplace transform of 1 over s squared, which is just t. And lowercase g of t is the inverse Laplace transform of 1 over s plus 2, which is just e to the minus 2s. Sorry, minus 2t, isn't it? Yes. Minus 2t. Okay, great. So now we want to think of what is f of tau. So f of tau is just tau. And then g of t minus tau is e to the minus 2 bracket t minus tau. Okay, so now we can put this together in the convolution theorem and say inverse Laplace transform of 1 over s squared s plus 2 is equal to the integral from tau equals 0 to tau equals t of f of tau, which is tau, g of t minus tau, which is e to the minus 2t brackets minus tau d tau. All right, so this one has a tau there and a tau up here. So this is one that we will do via integration by parts. Okay, so we'll say this via integration by parts. All right, and the way you do that is to represent that one which has a derivative that cycles around similar to itself. You want to write that one as a derivative, and that would be this. So we have the integral, and I'm going to keep writing, even though I'm going to change variables by substitution, I'm going to keep writing tau equals 0 to tau equals t, because otherwise I think it gets a little bit confusing. However, this is abuse of notation, because as soon as you make a substitution, you are meant to change this to the variable for which you substituted, right? Here we have tau equals 0, tau equals t. Okay, I'm going to write this as a derivative. So tau times the derivative with respect to tau of e to the minus 2 t minus tau, right? But if I actually differentiated this, I would then pull down, what would I pull down? A 2. I would pull down a 2 because I'm treating this as actually a partial, right? And so let's write this partially, just to remind you that it's a partial derivative, not a ordinary derivative. Okay, so if I actually did this, right, d tau is still there. If I actually took this derivative, I would pull down, via the chain rule, a 2. All right, so I need to compensate by dividing by 2. So I'll put this out in front, 1/2. Okay? Now, in aid to memory, we can make these vanish and say that this is just with respect to e to the minus 2 bracket t minus tau. And that's the way I want to represent this here. So 1/2 integral from tau equals 0 to tau equals t, tau d e to the minus 2 t minus tau. Okay, I'll remind you that even though this is done partially, we use the ordinary d here, and that is somewhat confusing, right? And again, this is abuse of notation here because I'm keeping this as tau equals 0 to tau equals t, when in reality I should do this in terms of my new variable here, where u would be equal to e to the minus 2 bracket t minus tau, right? So in other words, this would be from u equals e to the minus 2t to u equals 1, I suppose. I'm subbing in tau is t and those vanish, so I would get 1. Okay, but I'm going to leave it as is because I think it's less confusing this way. All right, so now we can use our integration by parts formula, and remember what that is. The integral of u dv is uv minus the integral of the other way around, v du. So that's what I'm doing here, pulling this out and this out. So here in this is our u, right? But it's a different u, right? So why don't we just say this is uppercase u here, when we're using the chain rule. Right, or substitution, as you would call it when you're talking about this in integration terms, right? And so this lowercase u is this one, and this e to the power of is my v, right? So I have it of this form. And so I take the two of these, I put them together, and multiply. But since we have a definite integral here, I've got to take some care. So we have 1/2. Now the product of those is tau e to the -2 bracket t minus tau. Okay, but we're evaluating this tau equals 0 to tau equals t. And then we subtract the other way around. So I carry my half through. And I swap these. E to the -2 bracket t minus tau d tau. Okay, it's very tricky, I know. So let's put in these bounds. So we have 1/2. We're replacing tau with t. So we have t. Now when we replace tau with t in here, we have e to the 0. So let's just put e to the 0 for now. Okay, now we're subtracting. What happens when we substitute tau in for 0? So because we have a tau here, we're just subtracting 0. All right, great. And then we're subtracting -1/2, the integral. So this integral is somewhat easy, but we do need to set out a chain rule or substitution, being this uppercase U substitution. Now you can pretty much do this in your head. So what we need to think about is what the derivative of this is. It's 2 when we differentiate that exponent with respect to tau, because we expand this and we get a -2 times minus tau gives us 2 tau, and so differentiating this would give us a 2. So I need to compensate by dividing by that 2. Okay, so then we have 1/2 e to the -2 t minus tau, and we're evaluating this between tau equals 0 and tau equals t. Okay, great. So here we've got a quarter. We can get rid of our 0. So we write 1/2 t for this part minus a quarter. Then we're subbing in t. Tau is t, so the exponent vanishes. So we've got e to the 0 minus e to the power. Now we're subbing in tau is 0. So e to the power of -2t. Okay, and so expanding this out, we've got we have a half t minus a quarter, because e to the 0 is 1, and then plus 1/4 e to the -2t. Okay, if I'm right, and it's really easy to get this wrong, then Mathematica should agree. So let's get on Mathematica and have a look at what it says. Okay, so I need to take the inverse Laplace transform of 1 over s squared, and then we have s plus 2. Okay, so it says that it is minus a quarter, there's our minus a quarter, plus a quarter e to the -2t, that's our second term, and then plus t over 2, that's right here. So Mathematica agrees, and so fantastic, because I thought that was pretty hard. Okay, next we have a very similar example. So this says use the convolution theorem to calculate the inverse Laplace transform of 3 over s squared s minus 2. So we want to set out, let uppercase f of s be 3 over s squared, and we've got that. Uppercase g of s is 1 over s minus 2, And so lowercase f of t is the inverse Laplace transform of 3 over s squared. And so that's easy enough because you can look this up in a table. That's 3t. Lowercase g of t is the inverse Laplace transform of 1 over s minus 2. And this is e to the 2t. Okay, so we need f of tau. And because this is tricky, because t and tau are, similar possibly in your mind, it's a good idea to set these out separately. So we have 3 tau, and then g of t minus tau is e to the 2 t minus tau. Okay, so the convolution theorem gives us the integral from t equals 0 to, tau equals 0 to tau equals t, 3 tau, this is our f of tau, and then e to the 2 t minus tau with respect to tau. Okay, so it seems like, again, we need integration by parts, but hopefully we can do this a little bit more quickly this time. So we want to represent this as a derivative, and so I can even pull the 3 out. But let's just put 3 over minus 2 tau d e to the 2 t minus tau. All right, and so what I've done here is I've skipped a couple of steps, because if you like, you can put this over d tau, so you recognize that you have a derivative here, right? And when you would differentiate this with respect to tau, a minus 2 would come out, right? So that cancels with this one. And so these two things are the same thing, but we do need to write tau equals 0 to tau equals t. Okay, super. So using integration by parts, we've got minus 3 over 2 tau e to the 2 t minus tau, from tau equals 0 to tau equals t. And then we subtract the other way around. So here I'm pulling out the 3 over 2 as well while I'm at it. And this time it's d tau. We're swapping these. And this is still tau equals 0 to tau equals t. Again, that's abuse of notation in this one, but not in this one. Okay, so let's evaluate this. And this is our inverse Laplace of fg. Okay, so continuing, we have minus 3 over 2 t e to the 0, and then subtract minus 3 over 2 times 0, because we're subbing in tau is 0 there, and that's out the front, so it's just minus 0. Okay, now with this one we can say plus 3 over 2. There are two minus signs. Now in our integral we have 1 on minus 2, right? Because if we would differentiate, we would pull down the minus 2. So going the other way, we divide. And if you like to set this all out, saying something like let uppercase U be equal to 2t minus 2 tau, go for it. Okay, so we have then e to the 2 bracket t minus tau, and we're evaluating this from tau equals 0 to tau equals t. Okay, and so let's put a bracket there because we have a minus sign, so we need to take a little bit of care. All right, so we have minus 3 over 2 t for that one. And then over here we have minus 3 over 4 for the product of these. And then this, we're subbing in tau, replacing tau for t. So we have e to the 0, and then minus e to the power of 2t. Okay, So e to the 0 is 1. So that's just minus 3/4 there. And then this part, we have 2 minus signs, so plus 3 over 4 e to the 2t. All right, now I can just ask Mathematica to please confirm this. Just need a minus down here and a 3 up the top. Okay, so minus 3/4, 3/4 e to the 2t, yes, minus 3 over 2t. Fantastic. All right, you know what, while I'm at it, just brainstorming here, I wonder, can we use the Laplace transform to integrate something? So let's just think about it, brainstorming here. So if y dash of t is equal to some function of t, right? And so I want to solve this differential equation. So the idea here is integrate f of t dt by solving this differential equation via Laplace. Can you do that? Okay, so if I remember right, taking the Laplace transform here, applying Laplace transform to both sides, we have the Laplace transform of f of t. Okay, now on the left-hand side, you can look this up in your table of Laplace transforms, but remind me if I'm wrong. So we have s uppercase y of s minus lowercase y of 0. And then on the right-hand side, we could call this uppercase f of s. Okay, and so now we want to take y of 0 over to the right-hand side and divide throughout by s. And so uppercase y of s is equal to, now you could call this a constant, right? So say let c be equal to y of 0. And so we have c over s, because we're then dividing by s, plus 1 over s uppercase f of s. Okay, so now what we want to do is apply the inverse Laplace transform to both sides. And so we get that this is y of t, right, which would be your integral, isn't it? Yes. Okay, so y of t is our integral. And so on the right-hand side, we have the inverse Laplace transform of c over s. Okay, so you could look this up, or you could just calculate it. All right, so we've got 1 for the inverse Laplace transform of 1 over s. So this is c. This part is c. Inverse Laplace of 1 over s f of s. Okay, and so this is just c plus the inverse Laplace transform of f of s times g of s, where g of s is 1 on s. Okay, so the answer is yes, but the question now is this easy or hard, right? Which one's easier? All right, so if, let's just pick a very easy example here. So let f of t be equal to 2t, so that y of t is the integral of 2t dt, which is t squared plus c. All right, and so this would say then that we can calculate y of t using the inverse Laplace of uppercase F of s, which is the Laplace transform of 2t multiplied by 1 on s. Okay, now what is the Laplace transform of 2t? Let's just look that up in a table, or you can either get Mathematica to calculate that for you, or do this via an integral. Okay, so for that, we have c plus inverse Laplace transform of 2 over s squared by 1 on s. And so we have then c plus the inverse Laplace transform of 2 over s cubed. Okay, so how about the inverse Laplace transform of 2 over s cubed? We get t squared. Right, so that is c plus t squared. And so the answer is yes, you can do integrals via the Laplace transform. Okay, so next we're going to look at the Laplace transform of a system of differential equations. And so just in case you don't know what that means, let's just for a moment take a pendulum. So I'll sketch a little pendulum here. And it's oscillating back and forth. And so we have an acceleration due to gravity. We have a damping force proportional to the speed. And we have a forcing function, say, keeping that going, right? Because eventually it would stop. Okay, so suppose then that we have a differential equation, theta double dash, where that's the angle theta, so the rate at which theta is increasing, decreasing, acceleration of theta. Suppose we have that plus theta dash plus 2 theta is equal to our forcing function, 2t plus 1. Okay, so then let's see, initially suppose we have theta of 0 is pi on 4 radians, and theta dash of 0 is minus 1. Looks like I've written on the page underneath that, oh well. Okay. Okay, so now what I want to do is couple this to form a system of differential equations. And so what I need to do is take these two items to the other side of the equation so that I have an expression for theta double dash. So we have minus 2 theta minus theta dash plus 2t plus 1. And then I, at this point, say let x be equal to theta dash, so that theta x dash is theta double dash. Okay, so then here I have x, here I have theta, and here I have x dash. So x dash equals minus 2 theta minus x plus 2t plus 1. Okay, now we also have theta dash is x. All right, and so if I shift the order of these, swap the order of these equations, and let uppercase x be equal to theta dash, so that uppercase x dash is theta dash theta double dash. Okay, so then I can write these two equations as a system forming a matrix equation. Okay, so let's see exactly what I mean by this. So we have theta dash, theta double dash as a vector or matrix. Okay, so x dash is this. Now what do we have here? Theta dash is x, so 0, 1 times x. Times the x would be down here, wouldn't it? Because that's theta dash. Okay, so this up here is theta. Now if I multiply this by this as a matrix, then I will just get back x, and so that is this equation right here. All right, and so in the second row, what I want is to get, because this is x dash here, so what I want is minus 2 theta. So here I need minus 2, here I need minus 1, so that if I multiply this out, I have minus 2 theta minus x being this. Then we have plus 2t plus 1, and so we deal with that by putting 0, 2t plus 1. Okay, there we go. So I've coupled this. Now theta x, or theta lowercase x, is just uppercase x. This is x dash. So what we have then is x dash is this 2 by 2 matrix by x plus this forcing function right here. All right, and so that's how we get what we have on the next page. This right here. Okay, and now here are our initial conditions, and remember what that was. It's theta of 0 and then theta dash of 0 being lowercase x of 0. So this is the linearized version of a second order differential equation for stamped pendulum. Now we can solve this using the usual methods of guessing a particular solution and solving for the homogeneous solution and adding the two results together, and then using our initial conditions to come up with this solution to the differential equations. So what we're going to do here is show that we can do the same thing using Laplace transforms. So we'll just use this to compare what we get here. Okay, so again we have theta dash is x, and x dash is theta double dash, which is minus 2 theta minus x plus 2t plus 1. So in other words, we just multiply this out and set out two lines, just like what we started with. Now we will let y subscript 1 of s be the Laplace transform of theta, and y2 of s be the Laplace transform of x, or the Laplace transform of theta double dash. But here we want to view that as the Laplace transform of x. Okay, so now on the right hand side we have 2t plus 1. So if we are taking the Laplace transform of both of these equations on left and right hand sides, then we will need to take the Laplace transform of 2t plus 1. So that is 2 over s squared for 2t and 1 over s for 1. Now applying the Laplace transform to both sides gives us this, but I'll explain a little bit more detail here. So according to our table of Laplace transforms, this would be s y1 minus this number pi on 4. Okay, and this one right here, Laplace of x dash, would be, because of this, we would have sy2 minus this number, so minus minus 1. Okay, now Laplace transform of x is y2. So this matched with this give us an equation in terms of y1 and y2. Similarly, we'll get, for the right-hand side of this second equation, we'll have minus 2 y1 and then minus y2 for this, and then Laplace transform of t is, as we said earlier, 1 on s squared, so we have plus 2 on s squared, and then Laplace transform of 1 is 1 on s. Okay, so these two, this equals this and this equals this, give us an equation in S, or two equations in S involving y1, y2, and s. So remember how we do. We solve for uppercase Y, but this time it's a system, and then we apply the inverse Laplace transform to solve the system. Okay, so simplifying, now you'll see what we have here. This, that's our y2, then over here, that's this. This right here is this, minus minus is plus, and then this right here is this. So we have this system. Okay, and we can rearrange this system by taking y2 over to the left-hand side and pi on 4 over to the right-hand side. Similarly, taking 2y1 over to the right-hand side and y2 over to the right-hand side. In the second equation, we have 2y1 plus s plus 1 in brackets, y2 equals 2 over s squared, 1 over s minus 1, because we take that one over to the right-hand side as well. All right, great. So now we have this, and so we can solve this system rather easily, say by eliminating one of these. So if we eliminated y1, we would want to multiply the first equation by 2 and the second equation by s, and then take a difference, for example. Okay, so when we do that process, we get these two things, right? And they look rather nasty. You now need to take the inverse Laplace transform of these, but easier said than done, right? I will show you one of these. And at that, I will show you some of the details of how you go about thinking about how to put that together yourself. All right, so taking this top one, right? So this is the Laplace transform of, what was it, theta. So this is y1. And we want to break this up using partial fractions, right? So since we have a product of something times s squared and something times s squared plus s plus 2, we can separate those as two separate denominators, but we have to be careful with our numerators so that when we put this back together, say via cross multiplication, if you like, then we will have a cubic on the numerator. That's what we want, okay? And so in the most general form, it looks like this: a1s plus a2, and then this one, b1s plus b2. So we multiply these across and put that all over 4s squared plus s plus 2, just like that. And so that looks like this. And so when you solve, because here is our left-hand side, our numerator of the left-hand side, when we match coefficients, so pi, for example, is a1 plus 4b1, and so on, we get these four coefficients in our partial fractions calculation. Okay. And so putting those back in, what do we have? Well, if we have an a0 there, then this is just 4 over 4s squared. So y1 becomes 1 over s squared. And then this one, we would have pi over 4s, and then plus pi minus 8 all over 4. Okay, and then this is all over s squared plus s plus 2. All right, now that's better than this for taking the inverse Laplace transform of, because we can now take the inverse Laplace transform of this, right, and get t. But this one is a little bit more tricky because the denominator there is not quite what we have in our table of Laplace transforms. So let me just find this among my pages. Okay, so have a look here. But it's most similar to this right here, this line. S minus a over s minus a squared plus alpha squared. So it should be something like this. We just have to find the a and the alpha. All right, and so to do that, we need to complete the square on that denominator. All right, so let me pull up another page and we'll go ahead and complete the square for s squared plus s plus 2. Okay, let me write this. S squared plus s plus 2 equals. All right, so I want to look at this part of it because that is almost a perfect square. So since I have a coefficient of 1 in front, half of this second coefficient, the coefficient of s, half of that is a half, right? So if I write this as s plus 1/2 all squared and expanded that, I would get s squared plus twice 1/2 s, which is s, and then I would generate something I don't really want, or something that doesn't quite match that 2. So I would generate a 1/4. So let's subtract the 1/4 that I would generate, and then we still have the plus 2. Okay, so it's starting to look a little bit more like what we have in the table, you know, one of these on the denominator of these, right? But we have to express this as a difference rather than a sum, and then we have to express the extra stuff as a square. Okay, so next, what is 2 minus 1/4? Well, that's 8 over 4 minus 1 over 4 is 7 over 4. So we have s plus 1/2 squared plus 7 over 4. Okay, now we can take square roots of this and express this as a perfect square. Now remember, we need to express this as a difference, so we have s minus 1/2, which is s plus 1/2, and then we have the square root of 7 over 2 all squared. Okay, so we have completed the square and we have expressed that denominator in the form that is in our table, something like this or this. Okay, so back to this page. We'll move on to the next page now. Okay, so this is the completing the square part that I did on that scratch paper, but you can probably fit some of that in the margin here. Now, so we've got our denominator set out in the way that we need it to be. So, like what we had in the table of Laplace transforms, so we're talking about this bottom, but for the top of it, the numerator, we need it to look like some number p times s minus 1/2 over that denominator, and then plus q times root 7 over 2, because that's what we have here. That's our alpha, right? And so let's have a look at our table of Laplace transforms. So in other words, we are looking at this one matching this, and this second one matching this, right? So that they would invert Laplace and give you e to the at sine of alpha t. So we've got to find p and q here. All right, and so you can do that just by multiplying your numerator out. In other words, p times s minus a half, or p times s plus a half, and then plus q times root 7 over 2. Match coefficients and solve for p and q. All right, so doing so gives you that p is pi on 4, right, because we have a coefficient of pi on 4 there. There's no other thing that p could be other than pi on 4, and q satisfies this, right? And so solving this equation for q gives us q equals pi minus 16 on 4 root 7. And so now we can put it all together. And so we get y1 of s is 1 on s squared pi on 4 times this that we know the inverse Laplace transform of, and pi minus 16 on 4 root 7 times this that we also know the inverse Laplace transform of. So now we can take the inverse Laplace transform of all three of those things. Okay, and so first applying inverse Laplace transform to those three things and then looking up what that is, we know that this one has a cosine in it and this one has a sine in it. And so we have t for the inverse Laplace transform of 1 on s squared. We have pi on 4 times e to the minus a half t. There's our minus a half. Cos of root 7 on 2. There's our root 7 on 2 times t. And then similarly, plus pi minus 16 on 4 root 7, e to the minus a half t, sine of root 7 on 2 t. All right, so there's our inverse Laplace transform of y1, and remember that was theta, so we now have a solution for theta. All right, and then similarly, we could do the same for y2. Okay, and we would get this. Inverse Laplace transform of y2 is lowercase x. All right, and so those agree with what we had on our earlier page that we calculated using other methods, right? So I'm talking about this. Okay, there's our t there, and then all of this matches these. We would just have to do some factorization.